Good evening, good morning, everyone. Good morning to Roger, especially. It's early morning for him. We are back again with our Wednesday knowledge sharing for good sessions. I hope everyone at your end, including you, are safe. On behalf of All India Oracle Users Group, we would like to welcome you to our weekly webinar session. Please pass this information about AIoG community to your connections and make it more successful, a vibrant networking community. And also provide your feedback. Without your feedback, we can't help you. We have so many things, so many ideas to support professionally. So please share your feedback after this webinar, and we will share the survey link. Today we have a great speaker, Roger McNichol, software architect from Oracle USA. He's a software architect in Oracle Data and Storage Technology Group. He has been working on core database internals for 35 years and Oracle for 15 years. He has worked on implementation of table scans, hybrid columnar compression, Exadata Smart Scan, Big Data SQL, and database in memory. Right? Roger is currently working in persistent memory support. Before joining Oracle, he was the architect for Sybase IQ query engine, the world's first commercial columnar database, and was the first chairman of TPCH subcommittee. So very warm welcome, Roger. Before handing over to Roger, I would like to remind you a few things. This presentation will be shared with you all, especially attendees, not the registered people. So whoever is attending this webinar, we will share via AIoG portal. You can go to the same page where you registered. You can find recordings as well as presentation. For all your questions, and there is a Q&A panel at the bottom of your screen, please use that, and Roger will take the questions appropriately. And don't ask questions in the chat window. Also, don't use Q&A for thanks, all these messages. So please keep it very specific to the questions to Q&A panel. Also, request you to take a picture or maybe once Roger start presenting, maybe you can take a screenshot of that presentation and tweet in Twitter. This is the only way you can connect with the other participants, or you can thank Roger, in the Twitter. I think Twitter is our virtual platform since we are not doing a face-to-face events. So please use that. And also you can use the hashtag AIoG webinar or AIoG virtual selfie, right? So with that, very warm welcome, Roger, and please go ahead and share your screen and start presenting. Thank you.
Hello, everyone. Thanks for the introduction. So you've already told everyone who I am. The only thing I would add is I'm actually very fortunate. I work from home on a farm in the middle of Lancaster County, Pennsylvania. I don't know if any of you have heard of an American community called the Amish, who still live like they're in the 1700s with no electricity, no cars, no modern technology. But we live right in the middle of Amish country, and both my neighbors are Amish. So when we live in a world that's so, full of hustle and bustle and stress, I look out of my window and see people going by in horse and buggies. And it's very de-stressing. So I'm very, very fortunate, and Oracle's very good about supporting people working from home. So this is a talk I give regularly around the world. It comes in 3 versions. I have a 45-minute version, a 90-minute version, and a 3-hour version. The 3-hour version is the one I do with live demos, but I'm afraid, I know many of you like live demos, but I apologize in advance that I'm not going to be able to do that today. But if there's enough interest, if you give feedback to AIOUG, maybe we, at some point, we could do a follow-up session with more live demos. So let's begin. So one more thing, just we will give this talk in 3 sections: regular table scans, which is about 45 minutes, Exadata scans, which is about 20-25 minutes, and in memory, which is 20 to 25 minutes. What I plan to do is take questions at the end of each of these 3 sections. So that should, with a 2-minute slot and a 90-minute talk, that should allow time. But many questions are, I find, are too complex to always do in a Q&A session in the middle of the talk, and more complex ones can be emailed to me or DM'd to me on Twitter, and then I can post the replies publicly on Twitter for anyone else who's interested. But people sometimes give me questions about individual bugs or things that need some research to follow up. I know a fair amount, but I certainly don't know everything. And I'm one of those people who prefers to research things and make sure I'm giving you a completely factual answer. So regular table scans, gonna break this into 4 sections. The query plan, buffer cache versus direct read. So the DBA, understanding how memory is used and the implications of that. How to trace table scans. I don't know how many of you play with Oracle tracing. I know many DBAs literally don't have time, but for those who can find the time, tracing is often the best way to understand what Oracle is actually doing. That, you can use trace file identifier to isolate your trace into an individual file, run one command, and actually look to see how Oracle actually did it. And a lot of understanding can come from that. So I will point you in this talk briefly to how to trace each of these areas so that you can, if you want, or if you are trying to solve a problem yourself, understand what is actually going on. And then we're going to talk about chained rows, which for DBAs have such a big impact on performance, they need a discussion. So enough with the clever plans. Sometimes, you can get straight to the data you want with an index or a materialized view. There are many ways that Oracle provides to get direct access, but sometimes you simply have to look through the entire table to find the information you want. And that's when you end up with a query plan that says table access full. And it comes in the 3 versions, which are the 3 sections of this talk. Table access full Exadata, which is table access storage full, and in-memory scans, which are table access in memory full. And one of the things we're going to talk about table access is Oracle has 2 different table scan engines. The row at a time driver, which was the only one we had up until Oracle 9i, and then the block driver that was introduced in Oracle 9.2. And this, one of the reasons that's so important is that only the block driver can use Exadata or in memory. The next slide is for the geeks, those who actually like more internals. If that's not your thing, you can just sit out one slide. So there's a lot of stuff happens when you simply say we're going to scan the table. In the top left of this screen, you see the row source. That is the bottom of Oracle's query engine. The Oracle query engine is a data flow engine. I don't know how many of you studied data flow in college, but it's a way of building engines that have from simple objects that support open, next, and close, and then you string them together to create a query plan. So the bottom of those query plans is a row source that scans tables. it may have to checkpoint an object, and we'll talk about why, and again, the implications for a DBA. The PQ coordinator, if you're using PQ, will also have to checkpoint. We're going to have to talk to the space management layer to get information either in extent order or row ID order. And that, if anyone who's ever looked at the view user extents, that is where that will be coming from. The table access itself has to talk to the transaction layer, and we'll talk about that. And then the cache layer, which manages memory, and we'll talk about the significance of buffer cache and direct read. And then finally, it has to actually talk to storage, which might be local storage, might be an Exadata cell, or it could even be remote, like object store. So the block driver, the Oracle 921, it was a complete rewrite that's designed to sit in a very tight loop, reading blocks, extracting the relevant columns, putting together the chained row pieces, processing first the cheap predicates, then the expensive predicates, and finally assembling lobs and returning the extracted information in either row or column format, depending on what the query engine has asked for. And one of the things that was so critical about this was anyone who's looked at modern CPU design knows they have very long branch prediction runs. So they hate lots of if statements. Modern CPUs run really, really well when they have very, very few if statements. And there is literally no application on earth that has more if statements than a database. And the thing that was behind Oracle's table scan performance improvements in 9.2 was that we found a way to remove all of those if statements, to have a way to generate specialized versions of scans that have, for all the different situations, that have those if statements removed. And CPUs are much, much happier with that and run much faster. We can't use it when rows need special handling. So that's when we fall back on the slower table scan methods. If you have long or long raw data types, we use the old engine. At this point, I hope most people have deprecated the use of long and long raw. They do, impose a performance penalty. If you are still using them, if you can navigate away from using them, that would be great. Anything that needs special handling of the SCN, the system change number, which is the internal clock that Oracle uses to keep track of time and order things correctly. So row versions query, where you select every version of a row between an SCN and an SCN, or between a timestamp and a timestamp. You can ask Oracle for the row SCN. That's the SCN where that block was, or row was last changed. Normally it's just the conservative upper bound of the whole block, but if you enable row dependencies, it is actually tracked on a row basis. So for example, you can run a query like select SCN to timestamp to see when each row was last updated. And flashback table scans needs the row at a time driver. So what about as-of queries? I don't know how many of you have used as-of queries, but they don't manipulate SCNs. Whenever Oracle runs a table scan, it takes a snapshot of the system change number, that moment in time when the query starts, that we want to see everything with a consistent view of the world. So normally it's the current system time, but if you do as of, it works as if you were running this query a few minutes ago, a few hours ago, depending on how much undo you have available. So every single query is an as of query. It normally is as of the current system change number. And this row driver is slower, partly because it returns entire rows unprocessed to the query engine. It doesn't push down the predicates, it can't use offload, it can't use in memory, it can't do aggregation inside the scan. So there's a lot of penalties for queries that do special SCN manipulation or that use the long raw data types. So more work that needs to be done is transaction management. One of the brilliant decisions that was made when Oracle was first created was to use optimistic transaction processing. So what happens in Oracle when I change a block, I do an update, I do a delete, we assume that transaction is going to commit and immediately write those changes to the block in memory and write the redo for recovery. And one of the really interesting things about Oracle's design that's quite unique was that when you do an update and insert a delete, those statements don't actually change any data. What they do is they generate redo, and then redo is applied to the block in memory. This is why Oracle can absolutely guarantee that if you crash and do recovery, you'll get exactly the same results as the first time, because the first time you did that update statement, it was actually done by applying the redo inside the engine. So it's one of the things that makes Oracle so robust transactionally. But the important thing then is, because other people's changes may have happened to a block, we need to see a version of the block that's consistent for us. So Oracle generates the undo so that somebody else's changes that haven't committed or committed future relative to our system change number can be backed out of the block. So that's part of the work that has to go on. And then the cache has a lot of work to do a scan. It's got to get the blocks, but if you're using rack, it has to maintain consistency across multiple sessions and rack instances. So recently, huge performance improvements have been made in recent versions of Oracle by using RDMA and cache fusion, so that blocks can be moved from the buffer cache of one rack instance to another with a direct remote memory access. Just directly get into the memory of the other rack and copy the block across with appropriate latching. But maintaining cache consistency can be expensive. So direct read was introduced many, many releases ago to bypass many of the costs of the buffer cache, but at the cost of having to checkpoint that table. And we're going to talk about that in just a minute. So buffer cache and direct read, two different ways of using memory when you do a table scan. Direct read uses PGA as opposed to SGA. The buffer cache is in the system global area. Direct reads set aside an amount of memory, a couple of megabytes of memory for each table you're scanning, of private memory. So this has an impact on PGA aggregate that the DBA needs to provide. Prior to actually doing a direct read, we have to do a checkpoint. Why do we need to checkpoint an object? Well, that's because when changes are first made, the redo is persistent on disk, but the latest version of that block is probably still in the buffer cache. And if we're going to do direct read from disk into private memory, we must make sure the most recent version of that block is on disk so that our direct read of it will see the most recent version of the block. In a data warehouse, of course, this is probably going to be a no. Not much is going to need checkpointing. You know, most data warehousing environments don't run with hot data. But here is something for the DBA to think about. And that is the role of partitioning. Why do we partition tables the way we do? Part of it is to get partition pruning from the where clause to eliminate whole sections of a table that won't be relevant to a scan. But another role that people don't often think about is the role of partitioning to isolate hot partitions from cold ones. So what you don't want to be checkpointing really hot partitions, because that will be expensive. So the idea is to size your partitions appropriately so that the hottest data will fit in the buffer cache, the entire partition, and we can use a buffer cache scan to get that partition. But as data cools, it can go into older partitions that can be checkpointed at reasonable cost. So when you're designing a partition layout, or you're trying to solve performance problems of scans in very hot OLTP systems, please actually spend some time thinking about how partitioning is going to interact with respect to how hot or how cold the data is. So Oracle doesn't actually think about partitions and tables. Those are, I think, what we call syntactic sugar. They're just labels to make life easier for the DBA. We only think about segments. A segment is a set of blocks, a set of user extents that could be a partition, a subpartition, or a table. And we think about granules if you're using PQ. A granule is how PQ chops up a table into sections to do in parallel. And when we're looking at table scans, we think of segments like t-shirts. They come in small, medium, or large. And that is how Oracle does its decision making. So a serial scan is going to go direct when simply it's smaller than the parameter small table threshold, which defaults to 2% of the buffer cache. And when that happens, we bump a stack called table scans short tables. Medium tables are ones, we have a parameter that something that can't be changed by a DBA called the medium table threshold, which defaults to 10% of the cache size, but is modified by how busy the cache is. And below 10% of the buffer cache will still likely bump table scan short tables. But a medium table is bigger than 10% of your buffer cache and smaller than an underscore parameter called very large object threshold, which is actually set very large. I think it's set too large. Talk about that just a second. But when we get to this size, above 10% of your buffer cache, we start looking at a lot more information, how compressed it is. We look at the percent currently in the cache, the percent of buffers that are dirty, current IO bottlenecks, rack access costs. And we'll either bump long tables or table scans direct read. But I said here in red, select for update has different rules. And it's interesting to think about why. When you do a select for update, like a search update, state update, where, or delete where, you're going to scan a table effectively twice. You're going to do a scan with the where clause to find the rows at your current SCN that meet your where clause. But then to change those rows, you don't want the current version of the block, you want the most recent version of a block. So those blocks will be essentially fetched again with the latest version rather than current version. So you want those blocks to stay in the buffer cache. So a select for update is skewed much more heavily towards trying to use the buffer cache and not use direct read for that first scan, the consistent read scan for the where clause. I don't know how many people still use the keep pool. For many years, keep was how Oracle allowed the DBA to say certain objects, try harder to keep these in memory than other objects. And that had a performance problem because, you know, as data grew, hopefully your business grows, you're doing more transactions, it could just fall out of the size of the keep pool. So we're trying to encourage people to stop using the keep pool, DB keep cache size, and switch to a new way of managing what stays in the cache. And that is DB big table cache percent target. We also refer to it as automatic big table caching. On rec, it needs parallel degree policy set to auto or adaptive. And the table size must be bigger than 10% of the buffer cache and smaller than this very large object threshold. What it does is it simply tracks the temperature of a table. So every time you scan a table, it bumps the temperature, but then the temperature ages down. So the object with the highest temperature will have absolute priority over the automatic big table caching area. So we basically try to work with you so that whatever is hottest automatically stays in memory without you as a DBA needing to think about, do I want to put this in the keep pool? Do I want to put that in the keep pool? How big do I need my keep pool list to be? Because when you start dividing up your buffer cache into things like a keep pool, it gives the buffer cache a lot less freedom to know how to use memory. So if you've not tried it and you have a test system, try testing by getting rid of the keep pool and using automatic big table caching. So if the hottest object partially fits, what we're trying to do with automatic big table caching is put the beginning of the table in memory. And then if it's too big for the buffer cache, we will slip over and change over from buffer cache reads to direct reads at the point where we're starting to see fewer and fewer buffer cache hits. So it gracefully moves over from buffer cache reads at the beginning of a table to direct reads at the end of the table. So another question that comes up is block sizes. I added this slide after somebody extremely incorrectly on Twitter said Oracle only tests on 8K blocks, which is not remotely true. So just for background information, we run our nightly regressions on a good mix of 8K and 16K blocks. We have many tests that run a test on every block size from 2K to 32K and ensure that consistent behavior happens with every block size. For reference, Oracle's OLTP stress tests internally run on 8K blocks, and our data warehousing stress tests mostly run on 16K blocks. But running with multiple block sizes, in my opinion, is a really, really bad idea. If you have multiple block sizes in use in your database, please note the bug on the screen and request a backport for it, because some of the decision making made with many different block sizes in use the mathematics was not quite right. If you're going to use 16K blocks for a data warehouse, then the entire database needs to be 16K, and that includes the data catalog. So that means right from the beginning, you have to create a 16 KB block database. So everything is consistent on that block size, and you're not splitting your buffer cache up into an 8 KB pool and a 16 KB pool. And even if you do change between these two block sizes, the performance impact is usually far less than many, many more efficient ways of improving performance. You might, if you're lucky, get 7 to 10% performance improvement on a data warehouse by going to 16K. You can probably look at the indexing you have and get way more than that simply by improving indexing or other things like that. So block size is not as important as people think it is. But if you're going to do with this, stay consistent with only one block size in the database. Now, that said, I did meet one customer. There's always one customer who says, you're wrong, blah, blah, blah. I know of one Oracle customer who has every single block size in use and a table with a partition of each block size. He has a table with a 2 KB partition, a 4 KB, an 8 KB, a 16 KB, and a 32 KB partition, because he's partitioning on row size and needed to manage locking. I think he's the one customer in the world that is the exception that proves the rule. But, you know, there are actually occasions, though they're rare, where having more than one block size in a database is legitimate. So tracing. Tracing to me is how I learn things in Oracle. If I want to understand how a piece of code I don't know works, I find out how to trace it. And then I do a simple statement, read the trace, and then I make my statement a little more complicated and look at the trace again. In the old days, Oracle tracing was done with numbered events. So if you wanted to trace, for example, to do memory tracing, KGH tracing, how we do our internal memory management, you would use event 10235, trace name, context forever, level, you know, whatever. We have making concerted effort in Oracle over the last few years to move away from numbered events and to use the new UTS, Unified Tracing Service. And the way that works is it's trace the name of a facility and then disk equals and one of 5 verbosities from lowest to highest. And the facilities to trace are arranged in a hierarchy. Now the top level, level 1, can't be traced, but levels 2, 3, 4 can. So for example, for a table scan, you can use KDS tracing, or if you just want full table scan, kernel data scan, full table scan, or row ID based kernel data scan RID. So you can either pick something lower down the hierarchy to trace it directly, or at the bottom line of the screen, you see KDS.star. It means pick up all of the children in the KDS family. So it's a lot simpler and easier to read when you see tracing like this, because you know what's being traced without having to remember what the numbers stand for. Tracing the decision to use buffer cache or direct read needs 2 things turning on together, NSMTIO and 10358, which together will tell you exactly why we decided to use a buffer cache scan or a direct read scan. If you do full table scan, I'm not going to talk through all of this slide. I want to point out just a couple of features. In the middle of the screen in blue, it says TD colon and a hex number. That is an internal handle to your scan. There are some query plans that may have several scans interleaved, and it can be very confusing to read tracing if you don't realize they can belong to different scans. So find KDS IRSF, the beginning of your scan, and you can recognize it because right at the top of it will be the SQL text and the SQL ID. And the SQL ID, of course, you can use to join then to $SQL and see a lot more information about how, you know, your scan was done. But you need to follow your TD, your handle, through the tracing to follow the stuff that belongs to just this one scan. With the buffer cache tracing, what you'll see is KCB, kernel cache buffer, and then first, is it a small object? And you'll see N blocks is the size of your segment, NBH is the size of the buffer cache, and PNB is the size of MTT, this medium table threshold. And then at the bottom, you'll see, yep, we chose direct read for this particular scan. And underneath ISM is small, you'll see IM is medium, and IVLO is very large object. So that's the 3 levels of decision making. So what happens when we add big table cache percent? Well, this scan went to direct read the first time I did it. Now I've defined big table cache percent, and you'll see some extra lines appearing. Serial DW scan, data warehousing scan, where you'll then see the PDB number, the table space number, and the object number. And now by defining big table caching, I get at the bottom of the screen, no direct read. So I've succeeded in moving this medium-sized table from being a direct read scan to being a buffer cache scan. So this is just one example of, how to use tracing. If we ever do a more hands-on one, I can talk through more what's going on and what's happening in the tracing. But I must talk about chained rows for DBAs. By the way, I love this GIF. For some, like the engineer in me just sits and I can watch this machine making metal chains for ages. It's just something very pleasing about its simplicity. To understand chained rows, we need to understand a little bit of how Oracle stores information on disk. A row in Oracle has 3 pieces, a head piece, a first piece, and a last piece. And at the beginning of a row, it'll have flags to say which pieces are present, and then a run of columns. But we can only store a maximum of 255 columns in a row piece. So if you've got more than 255, we have to create a chained row. Ignore the bit at the bottom. So we have head first, and then a next row ID, the first 255 columns, and the next row ID points to the next row piece for this row. And in this case, it's a last row piece, and it has the remaining columns. If you continue to do updates, you may get to the point where Oracle doesn't have space in the block, and it is more efficient to move the entire row into a different block, at which point you get what is called a migrated row. That's where the head piece exists all on its own with a next row ID, and that points to where the first piece has been moved to. The reason we leave this head piece behind is that is the row ID used by indexes. If we migrated the row and changed the head piece, the user would pay the cost of updating every index. And historically, we wanted to avoid that. And another kind of row chaining you'll see is very wide data. If a column can't be stored in one piece, we very reluctantly split in the middle of a column with something called a next row piece, an N row piece. We only do that if it's to avoid, I think, wasting more than 256 bytes in a block. But we try hard to keep columns in one piece together. But if you're storing 4 kilobyte varchars in line, you might see quite a few of these N row pieces. So why migrated rows matter for a DBA is head piece scans are needed when we need the row ID. If you're going to project the row ID, if you're going to do a select for update, a searched update statement, a searched delete statement, an index maintenance operation, you're going to need the row ID, which means we have to scan through the table looking for the head row piece. And then if it's a migrated row, there's going to be another buffer cache get and maybe a disk IO to get the rest of that row. And that can have a significant impact on the performance of scans. Regular scans don't need row IDs normally, and they just start with the first piece. So they're not impacted by migrated rows. Row movement enabled is one of the things you can specify for a table, but Oracle has historically very carefully and very deliberately not documented. It means roughly what we want it to mean in any release, but what it means in essence is you give us permission to change row IDs. So it must be set if you want to be able to move a row from one partition to another. But increasingly, what we're adding in performance improvements is that when row movement is enabled, we will try not to keep not to create migrated rows, but to move the head piece with the first piece, pay the index cost, but then all of the scans will be faster. For a DBA, column order still matters because of chained rows. If you put all of your most commonly used columns in the first 255 columns, they're going to be all in a single row piece, and you're not going to have to do a disk IO to get or potentially a buffer cache get that might be a disk IO to get the next row piece. So if you have you add a new column that you're going to be using very heavily and put it at the end of the table, and there's more than 255 columns, you've now had a big performance impact because you're doing another buffer cache get to get another row piece for every single row. Not a good idea if you can avoid it. It's worth analyzing how heavily your columns are currently used because applications change with time, and consider reordering columns to improve performance. And that can be done either with a create table as select or to do it online via DBMS redefinition. But the only way you can do that is if all of your insert statements used explicit column naming, so that if the order of the columns change, the insert statements work without needing to change them. So one of the things you need to manage is the people writing your applications, insert statements should always, always use explicit column naming for performance reasons. Percent free. This is the last big topic under regular scans. Something that people don't think about anywhere near enough, which is the amount of space to leave free during an insert for future updates. So by default, it's 10%. If you update a column to be wider than remaining free space, we move some or all of the columns to another block. What people need to think about is the row ID, row history, row life cycle. So you may have a row where you insert it at the beginning of an OLTP flow where certain things are not known, like the ship date isn't known, or credit card validation, or some other information that gets filled in later as the OLTP object is processed. And what happens then is things that were initially null when they're inserted become filled in, and the row gets wider. So really one of the jobs for a DBA is to look at the size of rows when they're first inserted by an application, look at the average size of rows at the end of the life cycle. So when all of the processing of that row has been completed, look at the difference in size between those two versions of the row, the initial inserted version and the final version. And that tells you what your percent free needs to be in order to stop performance degrading during the life cycle of a row. So I really can't emphasize this enough. I had a customer in London who shall be nameless, who had not set percent free, and for years had done more and more updates to a table, and every row was on average in 9 different row pieces on 9 different blocks. And they wondered why their performance really had suffered. One of the things that we see that really doesn't work well with Oracle is Java apps that insert a row that's all nulls and then go back and fill in any columns. It really does not the right way of using Oracle. And prior to 12.2, if you did that and you had more than 255 columns, it will really hurt performance badly. We have been making significant improvements to recognize these access patterns. But as it says in the picture, this is Stan. Stan didn't leave enough free space, and Stan's queries now run very slowly. Don't be like Stan. Last slide on this topic, deletes. Oracle maintains a high watermark of the last block used in a segment. If you delete a lot of data, it doesn't move the high watermark down. Those blocks still belong to that segment. The space is not reclaimed, And a table scan is going to be scanning those empty blocks each time. We know they're on the free list and have space in them. We don't know they're completely empty. So we still look at them. This is not ideal for performance. So if you have partitions, tables that used to be much larger and are now much smaller, you want to reclaim the space, because not only will it free up space, it will improve your table scan performance. And it can be done multiple different ways. Alter table shrink, which needs enable row movement set. Alter table move creates a brand new copy, but it's not online. There is an online version. And if you don't have the space left on the disk to actually have two versions temporarily, which alter table move will do, a way around it is to use data pump export and import, which will create a brand new clean copy of that table with every row laid out nicely and no wasted space. And it will reset the percent free in every block. So finally, we looked at tracing, and the last thing that you'll see for a table scan is stats. And these are the main stats for a table scan. How many index access rows, how many continued rows, that's chained row pieces that we had to get, how many blocks we got, how many rows we got, and how many of different kinds of scans, direct read scans, short table scans. Stats are interesting. They give you a snapshot of everything that happened for a statement or for a period of time, but they don't give you the granularity of tracing if there's a particular problem or bug you're trying to solve. Okay, so Q&A. We reached the end of section 1. What have we got? So question number 1, so every as of query uses the row at a time driver. No, the opposite is true. As of is the one that does not need the row at a time driver. So what it does is it simply resets the scan SCN to a different point in time, but every single query runs that way. So no, it's only the special SCN handling, like row versions or SCN that need it. Can you give some example of OLTP situation where partitioning can help improve query performance? So good question. That question actually right here probably deserves an entire AIOUG seminar on its own. And I know a couple of people who actually do talks on that subject. But briefly, what you're trying to do is think about two different access patterns, one of which is in your OLTP system, what reports are you running? If you're running reports that are just looking at the most recent day's data, the most recent week's data, partitioning by time enables the older partitions to be completely ignored by the query. And partition pruning can hugely improve performance because there's a lot less data to look at. And if you're running, monthly reports and things like that, where you want to pick up all of the data for 1 month, having partitions that fit with the boundaries of your reporting requirements, again, help the query engine only look at directly relevant information. And the other thing is this buffer cache versus direct read. By having your hottest information in partitions, whether you create a new partition each week or each day or every 4 hours, depending on how hot your system is running, trying to keep the hottest data in partitions that are sized appropriately for the buffer cache, and let as new partitions are created for the hottest data, the cooling partitions that aren't changing as fast can move over, be checkpointed, and use direct read. But Sai, I don't know if you've ever had a webinar on on how partitioning helps performance. But I think almost everywhere I go in the world, I come across people who would really benefit from a webinar on that topic. I hope that answered your questions.
Roger will keep in mind.
Okay, let's move on to the next section of this talk, Exadata. How did we get here? I mean, Oracle these days is very heavily based on Exadata. Our entire cloud runs on Exadata. And the story of how we got here, and I think that really helps you understand why Exadata, is in 2005, servers and storage were separated, and the bottlenecks between them came to completely dominate database performance. You know, I remember working at Sybase around the year 2000, and we were working on $1 million per terabyte for storage. And everything was about trying to cut down the disk I/O we had to do. Storage dominates the cost of database deployments in 2005, and warehouse queries were limited by table scans because it was like drinking from a fire hose. You were just scanning large numbers of blocks that had lots of rows and columns that weren't necessarily relevant. Red Brick at the time did a survey, we're talking late 90s, and what they found was that on average, a data warehousing query only accessed 10% of the columns in the main fact table, which meant 90% of the disk I/O was wasted. 2005, Oracle's a software company. We had RAC for a scale-out architecture for the database. We had scale-out architecture for middleware. We didn't have, no one had scale-out storage because everything was limited by the connection from storage to the main computer. So what we needed was not just scale-out storage, we needed smart storage, retrieving only data of interest from disk. And I put in red here, in software, not hardware. You know, as I said, I've been in database core development for 35 years. It certainly made me feel a little old. And I suspect I'm the only person here who remembers ICL in the 70s had something called CAFS, Content Addressable File Store, where they tried to get disk I/O to only return relevant information by putting filtering directly in the disk head controller. It was horrendously complicated. You know, every time you had a new disk drive, you had to re-implement the filtering. It was a brilliant idea. The technology, though, physically didn't exist to implement that idea that they had in a good way. So we learned from that. Doing it in hardware didn't work, doesn't work, is never going to work because the maintenance costs are too high. We needed to do it in software. And around this time, 2005, you know, Intel CPUs had been growing in leaps and bounds in how much work they got done from law. So we decided to put CPUs directly in our storage layer to do smart filtering. And what happened was Cody, who's one of the most brilliant engineers I've ever worked with, took a whole load of old computers that Oracle had junked. They were in a storeroom for junked hardware. He built a prototype of Exadata using this old thrown away hardware and showed management it worked faster than Oracle's brand new, extremely expensive SAN. And at which point they said, we've got to implement this. And that's how Exadata was born. And Exadata has grown fast. And in terms of table scans, its performance has grown very fast indeed. You know, with V2 in 2009, we first added Flash on SCSI, and we're getting 50 gigabytes a second. With the X5, we moved to NVMe attached Flash, and we jumped 260 gigabytes a second. And with the X8, we're now up to about 560 gigabytes a second. I mean, you're not going to put that 560 gigabytes per second on any kind of interconnect. So the need for smart storage has grown exponentially with the improvements in flash arrays. So if you have a flash storage array, it can share flash capacity, but not flash performance. So as we've just said, we need to move computing directly to the flash. And the only way to do that is if we own the entire stack, because otherwise you'd be re-implementing everything all over again for every kind of storage layout. By creating a complete stack, we can control the entire stack from top to bottom and make sure everything's only implemented once and works together. It's like the difference between owning an iPhone and an Android cell phone. You own an Android cell phone, they're kind of anarchic. You know, every manufacturer rolls their own. You're kind of on your own with what you do, and you download apps, and you know, it doesn't work so well on this Android, but it works really well on that one. You buy an iPhone, it costs a little bit more, but everything has been tested top to bottom, and much more reliable. So Exadata is like an iPhone in a way, just a very big, very expensive iPhone. So blocks are full of unwanted information. If you look at this overly simple query, select sum of C2 where C5 is greater than 100. We have a block here with rows in and columns. The predicate where C5 greater than 100 will select just this one row. And we see the columns, but once we've done that predicate, C5 greater than 100, there's no more references to C5 in this query. So in fact, the only thing that's needed after that is the column C2. So from this particular overly simple example, instead of returning this whole block, we only have to return one single value, which is column 2 of row 3. So you've gone from putting the whole block on an interconnect with the old way of doing things to writing a very, very small block of just the relevant information to send to the table scan when you have smart storage. That is the idea that Exadata is based on. As I said, in order to use smart storage, it has to be the block driver, and row major tables are limited to 255 columns referenced in the query because of row chaining issues. The things that can't be offloaded to storage is anything that has to run directly inside the RDBMS engine, PL SQL, system functions, some aggregates, analytics. But also, now here's something for the DBA to think about. When you have a where clause, unlike some other databases like Sybase, Oracle doesn't rewrite the where clause into conjunctive normal form. So if you have a mixture of predicates that can be offloaded to Exadata and ones that can't, you need to make sure the ones that can are at kind of like at the front of the where clause, and move things like system functions or PL SQL functions to the end of the where clause if you can, simply to allow more of it to be offloaded. LOBs, for those who have used Exadata for a while, support for offloading of inline LOBs was added in 12. Expressions on LOBs like regexp, compressed and encrypted LOBs have been supported, XML CLOB and JSON. Oracle has a limit of 4 KB inline. You can create a 4 KB varchar 2 and then do alter table up to 32 KB, and it will stay in line because there's no LOB segment. Not a terribly good idea, which is why we don't document it. In 21C, we've actually done a lot more work on Exadata working well with more than 4 KB inlined. but with the introduction of the new JSON data type that inlines up to the block size. So if you have a 16 KB blocks, you can get up to 16 KB of JSON inline on Exadata Smart Scan. You can actually control what gets offloaded to Exadata. There's a view SQL function metadata, and you can actually change something to not be offloaded with opt disabled, and then it's function ID from that view. The only time I've ever had to tell a DBA to do this was this DBA had a user who liked writing really toxic regexp expressions that were computationally so hard, it really was affecting the performance of everyone else on the system. And the DBA just said, okay, regex, we're not going to offload it. And the problem disappeared. But that was really to handle, in my opinion, a user who was willfully not being helpful. But every DBA has encountered users like that at some point in their career. And the way it works with CDB is if you have multiple versions of Oracle in use, and many, many, many customers have multiple versions of Oracle in use, what Oracle does is in the storage layer, it has one central cell server, which manages storage index, flash cache, IO, and then it spins up offload servers for each version of Oracle it's in use. So, if you start using, 18 in the middle of this, it would just spin up an Oracle 18 offload server in storage. And starting them and stopping them is managed automatically under the covers. So Smart IO, we're aiming to speed up your queries, and by adding both horizontal and vertical parallelism. So horizontal, because it is concurrent processing of many Smart IO requests, and it's vertical because the storage servers are processing more blocks while the database is consuming the cut down versions of the blocks already returned. I'm going to skip this thing in the interest of time to go straight to the picture of how it works. The database is talking to ASM, and a table scan will ask for an ASM allocation unit. It's 4 or 8 megabytes. That request gets sent to the Exadata storage cell, which chops the request up into 1 megabyte disk IOs. And the filter processing library is given a megabyte's worth of block and a 1 megabyte output buffer. And it slices and dices the blocks into the output buffer. And those are put together and sent back. So all of that is happening asynchronously, so it handles skew very, very nicely. So each 1 megabyte returns its cut down results, if there are any, in an output buffer. And they have to use direct read because they don't match anything on disk. They're completely cut down. They're free length blocks because they contain only the data that was directly relevant. And if we project expressions, they go in an auxiliary output buffer. So sometimes we can project, 1 plus tax directly in out of storage as well. One of the things that I did in 12.2 was row major blocks in storage can be returned in columnar format. And you don't need an IMC license for this. This is totally independent of in-memory. Because the query engine can use columnar data far faster than it can use row data. So when you have row data on disk, Exadata will return that row major data in column major format to the query engine, which again gives a performance improvement. But what is the significance of these 1 megabyte chunks? If you have a lot of row chaining, We can only process the row if we can see all of the row pieces. Now, when you first insert everything, those row pieces will all be in contiguous blocks, and that's going to work. If you haven't left enough percent free, row pieces are going to move, and it's going to look for space on the free list and probably find it in a different 1 megabyte chunk. And Exadata will say, I don't have all of the row pieces. I just have to send this block back unprocessed, which has a negative impact on performance improvement. So again, percent free, if you've got a lot of updates in the life cycle of your rows, it really is important to think about the change in row size. Make sure percent free is big enough, because it has an even bigger effect on Exadata than it does on non-Exadata. We have done a lot of changes to try and keep, during updates, keep row pieces within a 1 megabyte area. But just one thing to add from this same version of the slide that we saw earlier under chained rows, alter tables shrink space compact before Oracle 12.2 was doing the wrong thing for Exadata. And it was rewritten in 12.2 to be aware of this 1 megabyte chunking and keep rows together within 1 megabyte chunks so that they work nicely with offload. So reorganizing data, we're just back to our row chaining. We have 300 columns. It's going to be stored in 2 row pieces. And if you're very unlucky, it might become a migrated row. So if my query now accesses column 260, I will jump over the first 255 columns, start at the next row piece, and then work my way through the row, one column at a time, till I get to column 260. And when you're running data warehousing queries, you really want a faster way to get to information. So if you think of a block full of rows, you can imagine that's an Excel spreadsheet, and we pivot it. So instead of rows, exactly the same information in the same space can be viewed as columns. Well, that gives us very short column runs to work on. Can we do better? Well, what happens if we take several contiguous blocks and create a super block? So we take 4 8 KB blocks and or 8 of them and view them as a larger super block. And then pivot those set of blocks together. And that was what we called hybrid columnar compression. When I was at Sybase IQ, working on pure columnar databases, they were wonderful for data warehousing. And we sold the IQ into a lot of Oracle sites to do data warehousing queries. But they were terrible at row-based operations because you had a disk I/O per column. What you really want is to enable a direct row read or a change of one row to be done with one disk I/O, but still get columnar processing. So that's why we came up with hybrid columnar compression. So we get nice long column runs that compress very well, and predicates run them on them extremely fast. But you can still get at a row with a single disk I/O. But that still left us with the problem that we were doing the disk I/O for the columns that were not needed. And we got some criticism in the press for the fact that hybrid columnar was still doing this disk I/O. So Juan Lueza and I came up with this idea of the column cache. Take 1 megabyte's worth of blocks, so a complete chunk that Exadata would process, and run it through the in-memory loader. And again, we'll talk about it. You don't need an in-memory license for this if you're on Autonomous. So it takes 1 megabyte, runs it through the in-memory loader, and writes it into Flash in pure columnar form. This enables us to only do the disk IO for the columns that are needed. So we have our rewritten 1 megabyte. The query gives us a bitmap of which column IDs we want. And then we go to the hash table that manages flash storage, find the beginning of the chain for that 1 megabyte address and follow the linked list. And it tells us which 64 KB flash pages are holding which columns. And we only read the flash pages for the columns that are directly of interest. So once something's been moved into this format, the amount of disk IO can be drastically reduced. And again, big performance improvement for table scans. So as I said, this column information, tremendous reduction in disk IO. That means there's less memory, less mem copying costs. But another thing to think about, the CPU data cache, when it gets into the CPU, you normally if you put a row from an unprocessed block in a CPU cache, it's got all of the columns you want and all of the columns you don't want in your L1, L2, L3 CPU cache. By removing all of those things that aren't needed, the CPU cache in a database now is used only by things of interest. So your CPU cache rates, the L1 and L2, L3 cache rates go up tremendously. There's a lot fewer pauses to move memory around. Another performance improvement for pure columnar is instead of having to decrypt an entire block, you now only have to decrypt the columns that are needed. And remember, in autonomous, everything is automatically encrypted. And then one last thing that I did. Storage index is used by as a way to cut out disk IO. We store the min and the max and whether there are any nulls for columns we frequently see in predicates, so that if we see a predicate, we can say, does this block have any values of this column that are within the min and the max? And if not, we don't even have to do the disk IO. We just discard that whole 1 megabyte. That doesn't help you in a situation like this. And I apologize, I didn't have the time or the knowledge. Maybe Sai could help me afterwards come up with an Indian version of this. But America has 50 states with codes from Alaska to Wyoming. And if you're a business in the Southwest, your states, are this run from Arizona to Utah alphabetically. So I'm a company in San Francisco. I just sell to local states, and I have 6 states that I'm selling into. Min and the max is not going to help me because I may be looking for California data or Nevada data, and there's a whole range of things, but there may be none of that one state that's in the middle between Arizona and Utah. So regular storage index can't eliminate this disk IO. So what I did with the storage index was added very, very dense Bloom filters, 250 bytes. So they're only usable with up to 220 distinct values in a column. But we hash the values that are present in that 1 megabyte and store it in a very dense Bloom filter. And then when the predicate comes in, we hash it. And if the bit isn't set in the Bloom filter, we know there's none of that value in this 1 megabyte. So this one block here had Arizona, California, and Nevada, but there weren't any customers in Colorado. And I'm trying to run a report on Colorado. So I can eliminate this entire disk IO. Again, has a big impact on table scan performance. And then the last slide is how to trace it. For those who want to trace it, you're tracing the storage cell. So the tracing has to be done on the storage cell with alter cell offload group events. And this is the syntax for it. If you're doing it directly in the tracing, will be under ASM because ASM is controlling the cells, and then cell, then the version of the cell that's running and a trace directory. More recent versions of Oracle, if you set the this fplib tracing in your main session, it will pass it from the RDBMS to the storage cell to trace just that one session instead of tracing the entire storage cell. But again, it can be, so if you want to understand the storage cell, it is, and you've got a recent version of Oracle, it's worth doing that. Say, set trace file identifier, set fplib tracing, filter processing library tracing, run your one statement, and then reset trace file identifier. And then you can go to the storage cell and see how storage processed that one statement that you ran. And just lastly, what you'll see in stats, you'll see a section in stats for cell blocks that were processed. Now, something to look out for here is processed by cache, transaction, and data. If blocks are being rejected by the storage layer for either because blocks were corrupt, they couldn't be decrypted, or they were transactionally needed undo applying, which needed the RDBMS, you will see the number processed by each layer go down. In a nicely running system, they will all be very similar numbers. So again, you can work out some kinds of performance problems, particularly related to transaction management, by looking at the cell block statistics. And down at the bottom, there's a couple of interesting ones that tell you how much the disk IO was needed and how much it was cut down by what was returned by SmartScan, but also the impact that the columnar cache, which did a lot in this query, and storage index had, which wasn't used in this query. So those are the things that control performance for Exadata scans. And that brings us to the end of the second section. Do we have any additional questions? Vivek asks, what about HCC compressed table with more than 255 columns? No, the restriction does not apply. One of the reasons we did HCC was to get rid of row chaining. So instead of having row chains, HCC uses a set of blocks that are forced to be adjacent to each other and aligned with the 1 megabyte boundary. So even if you have 1,000 columns, you'll never have a restriction in Exadata. Okay, that's the last of those questions. If people are ready, we'll go on to the shorter section, since I have 10 minutes on in-memory. So I don't want to rehack slides that people have probably seen many, many times, which is storing stuff in rows and columns simultaneously at the same time, because some things work better on rows and some work better on columns. What's interesting for me is the history, having worked on pure columnar systems. If you go right back to the early days of database, you know, Ted Codd back in 1971, doing relational theory, disk IO was even more dominant as a problem. You know, you had 1K or 2K blocks. Everything was about the minimum amount of disk IO, which meant that was why data is stored in rows. It goes back to only being able to do a single disk IO to read or write something. And a very small block, because again, that was a hardware limitation. And so that was, you know, dominated by locking costs, by large numbers of users, and reporting really was a very poor cousin who, you know, only got to look in afterwards when the OLT people had got everything they needed. Queries were a huge problem. Pure columnar came along and said, well, what happens if instead of making the person reading and writing information most important, we make the person running the query the most important? Then what would you do? Well, then you'd want very large pages on disk. You'd want data in pure columns, so you only do the disk I/O for the columns you want. Pure column data compresses much better. If you have ever studied compression algorithms, they work really on what's known as the entropy of information, but that's kind of a hard concept to explain. I think of it as the surprisiness of information. If you're driving a car and you come to a T-junction with a turn left lane, a turn right lane, sorry, a crossroads, and a straight on lane, if I'm in the turn left lane and I turn left, that's not surprising. I can use one bit to say that. If I'm in the turn left lane and I go straight on, that's a bit more surprising. If I'm in the turn left lane and turn right, that's really surprising. And if I'm in the turn left lane and do a U-turn, that's kind of the most surprising of all. And as it gets more surprising, you need more bits to encode it. It's like basically one bit says the expected thing didn't happen, so my next bit says something that was more unexpected, and so on. So the more unexpected it is, the more bits you need to say an unexpected thing happens. So if I have a column of all numbers, they aren't changing very much, and compression algorithms like that. Or if I have a column of all names, they compress really nicely because the information to a computer algorithm is not surprising. So again, you're aiming to get very good compression, but in the modern world, you don't want to decompress in order to actually run your predicates. So they're heavily based on semantic compression, compression that does not lose information, and you can directly do predicates on it. And then you can do bitwise compression like LZ, zlib, LZO, zstandard on top of that for a second round of compression if needed. So what we're doing within memory is so the column cache in Exadata was just rewriting 1 megabyte. In memory gets back to the real world of pure columnar, where we're rewriting 500,000 rows at a time to get really long column runs so that we can use SIMD instructions to process them. And with SIMD instructions, we can load large numbers of column values into a SIMD register, issue a single compare, and output the results of all of those predicates in a single instruction, which really gives us tremendous value. And at the beginning of this, Intel didn't have all of the SIMD instructions we needed for database work because SIMD had been designed more for video work. So the last few years, we've been working with Intel to add more database SIMD instructions to the CPUs themselves to enable Oracle's in-memory scans, table scans, to run faster. But so here's something new for the DBAs. You're used to PQ. PQ can have status queue problems where the way things get distributed leaves one PQ slave with a lot more work to do. With in-memory, we added in-memory dynamic scans, which use p-threads. They use internal lightweight threads to break work down into a way that's parallel, that doesn't have problems with data skew, because it is just lightweight threads that can move around quickly. So what we now do is we add, where it's appropriate, these in-memory dynamic scans on top of PQ, or if it's a serial query instead of PQ. So each in-memory compression unit can be handled in parallel by a lightweight thread. And this gives much better table scan performance because thread 1 can be working on the first IMCU, thread 2 on the next IMCU, and so on. And I'll talk a bit in a minute about how to see when this is happening. So the first way to see it's happening is with stats, IMScan dynamic. So you can see when an in-memory dynamic scan kicked in by the IMScan dynamic stats. So that's one way to do it. The next way is tracing. And you've probably gathered by now, I love tracing. The trace event is IMScan. If you also combine it with the KDS full table tracing scan, you will see a KDSTF method with a specialization that says is IMC. So KDMS is kernel data memory scan, and you'll see a start down to an end where it will get in-memory compression units from its metadata, fetch them from the pool, do a transaction get to make sure that they are consistent for your worldview, your scan SCN, which then assemble the consistent version and process them. When this in-memory dynamic scan kicks in, and for your table scans, and you want to understand it, you'll see KDWS in it to KDWS end, where now you'll see submit, process, and complete as the pthread tasks are picking up in-memory compression units, processing them, and then reaping the results back to the main thread. So that's how to see what is going on under the covers within memory dynamic scans. So how do I see what's in my object store? Well, I've got $IM segments that I can check to see if something's fully populated in memory, and if it fitted, or bytes not populated will tell me it didn't quite fit. But now what's going to happen if I delete some rows or I update some rows? What we do is we store, in order to improve table scan performance, an invalidation bitmap for each column. So back to my update statement, set C2 equals 0 where C5 greater than 100. When I run this, row number 3 is now invalid in the in-memory store. The version in the in-memory store is not the current version. And this bitmap, of course, is partitioned by SCN. So for your particular SCN, we know whether it's valid or not. What will happen is we will run the in-memory query to completion, and we will use this invalidation bitmap to remove rows which are no longer valid because of updates. And then at the end of the in-memory compression unit, we will do a second phase of the scan, which you'll see in tracing as DIMC, disk IMC, where the invalid rows will be fetched by row ID from the buffer cache. And if the buffer cache is sized well, blocks just changed by an update statement are still highly likely to be in your buffer cache. So that means it's the buffer cache get, but no additional disk IO. It's still running in memory. So that really is how the design of, so updates and deletes can keep going while scans continue to use the in-memory store. And then internally, we track how many invalid rows there are. And when it reaches the threshold, we repopulate that in-memory compression unit under the covers. So what happens if it only got partially loaded? I had space for half my segment. Well, it's not, certainly before Oracle 19 or 20, it's not a cache. So it's not going to evict something else to make space. So what we do is we look to see how much is in memory. And if we've got at least 80% in memory, we'll use an IMCU scan and then switch to buffer cache, or we'll switch, if there's less than 80% in memory, we'll switch to direct reads. But something I want to introduce you to for performance management is hybrid plans, table expansion plans. If you have some partitions in memory and some not, what you risk finding is when a partition moves out of memory, suddenly the queries on it, on that partition, performance drops by a significant amount. But equally, when you've got an in-memory area, you don't want to be maintaining large numbers of indexes that are only used for data warehousing, because you don't need those indexes when you can do in-memory scans at extremely high speeds. What you want is to have those indexes on the partitions that aren't in memory and not on the partitions that are in memory. And that is one of the things that we created partial indexing for. You can declare index to be partial. And then when your partition is aging and you're going to move it out of the in-memory area, you can do alter table modify partitioning indexing on. That will now build your data warehousing indexes on that partition, because you'll still have needed your OLTP indexes. This is really just for the DW indexes. So when it's built, you can then do modify partition no in memory. So now we've got, it was in memory, but now it's indexed. What will happen is that Oracle will create a table expansion query plan. It will split the query plan into a table access full on the partitions which are in memory, and index range scan on the partitions that are indexed, and then union the results of those two different scans together to give you the result of your query. So now, as a DBA, you have a way of managing performance smoothly as the storage gets tiered for in-memory to out of being in memory. So create index indexing partial, and then modify partition indexing on off. It is one of those features that isn't talked about enough and certainly isn't used enough. If you've got a test system, I would advise you, as a DBA, as part of your skills learning, to try playing with indexing partial on partition tables. It can be an incredibly useful feature for managing the performance of queries across the information lifecycle. So even without in memory, so you're not paying the cost of maintaining data warehousing queries on really hot partitions, but as partitions cool, you can start maintaining your DW indexes on them, because you're not going to have the index maintenance costs from DMLs. So again, a very useful tool for the DBA for managing performance across the information lifecycle. And that brings me just on time to the end of my talk. So as I expected, we had most people stayed right to the end of the regular table scan, but then people weren't interested in Exadata and memory dropped off. But I appreciate the fact we've still got 80% of you still listening, and I'm grateful for that support. Best ways to contact me. I'm Roger McNichol on Twitter. Part of my job is supporting users. Send me questions. I don't know the answer to everything, but I almost always know who does know the answer. My email address is just my name, roger.mcnichol@oracle.com. And I have a blog, which is the Oracle Smart Scan blog. I'm a bit behind on blogging and I need to catch up on that. Sometimes when people send me really interesting questions, I turn them into answers on the blog, because that's the best way of getting the answer to more people. It's like, oh, well, if he asked that question, probably a lot of other people are asking it as well. So I blog the answer. But I am here, particularly for the DBAs, I'm here to help. I'm here to help you be more successful in your job. I'm here to help you have a better experience using Oracle. So don't be shy. There are no stupid questions. So with that, I will pass back to Sai.
Thank you. Thank you, Roger. I hope I'm audible. Sai is not that this is Vinay from All India Oracle Users Group. I would like to thank Roger for your valuable time for uh, uh, for conducting these sessions. We definitely would like to deep dive these sessions, as we know that there is a three-hour session in your Pandora's box. So we will definitely go there. uh, Maybe we'll have a follow-up session on this. You can thank Roger on by tweeting on Twitter. That is his Twitter ID. Do send in questions on Twitter. He'll be happy to answer. You can also send your questions during the speaker's feedback. You can see the QR code here. You can just scan the QR code, or just at the end of the session, once you leave the session, there will be automatically a feedback page appear on your screen. Please take out few minutes to give the feedback so that we can we can get better and better topics in coming times. So here is the next sessions coming up. There's a session by Maria, who is product manager. She will be discussing on best techniques for generating an execution plan, along with understanding cardinality estimates and different access and join methods. She'll also cover join orders, partitioning, and parallel executions. So a very good session. Please make sure that you register in advance so we understand how many people are going to join. Uh, a session after that is on 9th of September. Is by Rob. Rob is an Oracle Ace director. He'll be discussing on Oracle security in cloud. This session will help DBAs, developers, and designers to set a checklist for their database securities in their various roles. So do take out time. As again, I would like to say, please make sure you register on the AIOG portal. The presentations for these sessions will be available to all attendees on the AIOG portal itself. Go to the same webinar and you'll be able to see the presentation area. With that, thank you, Roger, once again, and
Oh, thank,
definitely
and
we'll
thank you
meet.
for inviting me. I appreciate the chance to join with you all, and I hope one day to actually attend AIOG in person.
Definitely, definitely. Due to pandemic, we don't have it this year, but definitely we would love to have you in the next year in one of our flagship events. Thanks a
Great.
lot for your time. Thanks, guys, and we sign off. Thank you.